Welcome back to another exciting chemistry lesson. In the previous lesson, we learned how to write the rate law for the overall reaction based on the elementary step by applying these rules right here. That is, each elementary step is reversible. That means it's only go one direction, or the first step is a limiting step, which is the slowest one. But in this case, we are going to look at a situation where this rule does not apply. So in this example here, we have this overall reaction broken down into two steps. The first step is not the slowest, so you cannot use that part, and it's also reversible. Now let's look at reversible reaction. What does it really mean to be a reversible reaction? A plus A, okay, going this way and going that way, give you B. So what we have here, of course, is that going forward, we have the K constant going 1. Just use basic math, right? What's the opposite of positive 1? Well, opposite 1 is negative 1. So when we have reversible reaction, this become a reactant. This can also become a reaction as well. So what we have here is rate of forward equal to rate of reverse, right? Forward, reverse is reversible. So now let's write this in terms of rate of forward, which is from reactant to product, okay? So remember, when we go the opposite direction, the product becomes reactant, so keep that in mind. So we have K1, just to illustrate going forward, okay? But again, K is a constant, it does not change. So the reverse and the forward have the same values. All the constant in the same reaction is the same. That's why we call constant. So what we have here is A to the second power. Remember, this can be rewrite as 2A like that, equal to the reverse reaction rate, which is K equal to, there you go. Isn't that nice? So I just write it like that. So we have our equilibrium in rate law. The forward equal to the reverse. The next thing we need to do is we need to focus on the slowest one. In this case, there's only 2. So this one is the one that's going to be the rate determining. And what we need to do is we need to write it out in terms of, let me write this out. B equal to C, D right there. So here we have B plus C equal to D. So for the rate law, in this case, you look at this, this is the step 2. So we're going to label this. This is going to be K2. Again, all the K are the same. We just want to represent so that way we can keep track of it. So we have K2, B, and C. Look at that. Notice how we have B and C here. So what we can do, we can substitute B over. But before I do that, let me isolate B over here, okay? So if I do this, B is equal to, see how I just bring it over? See, I just bring this over here. There you go. So what we have here is rate equals to K2 time K1 A squared K1. There you go. And that times C. See how I would just substitute this in here into B like that? I just copy and paste to some extent. Now we just need to simplify it. So I'm going to K cancel out. Look at that. K cancel out. Remember, all the K are the same, okay? So K1, K reverse, K2, same, because it's the same reaction. So now if we simplify this, what is our rate law? It's going to be K2, A to the power of 2, and C. And that's all we have to do. Isn't that nice? But again, we're not going to use the word K2. We're just going to write a general K. A squared equal to C. If we are to type in our computer K, A, the caret 2, and then C. There you go. This is how you would type in a calculator to represent this as an exponent number. Now let's try a very challenging question, so that way all the other questions will become very easy for you. As you can see here, we have 3 steps, and right away you know this is not going to meet the requirement because the first one is the fast and it is reversible. In this case, what we have here is, of course, we have 3-step, but which one are we going to use? Of course, just the equilibrium, and we focus on this one. We don't really care about that part, okay? So now let's write this out. So what we have here, of course, is K1 and K reverse, okay? So I'm going to write this over here, okay? So rate of forward is equal to rate of reverse. If that's the case, we have K of 1, which is forward, okay, equal to CL2. Isn't that easy? And over here, going backward, we have K of reverse equal to, and we have the coefficient here, multiplied by CL and the coefficient up to the power of 2. There you go. And that's pretty much it. Now let's go to the next step where we are going to focus on our slow one. So if that's the case, let's label this as K2. How about that? So rate of 2 equal to, what we have here, of course, is K2. Again, all the K are the same. We're dealing with the same chemical reaction, okay? Cl and CHCl3. What do they have in common? Well, they have Cl in common. So let's go in and change our color. So Cl is in common. So we have to isolate Cl. If that's the case, we bring this over here, isn't it? So we have K1 Cl2 divided by K reverse equal to Cl to the power 2. Ooh, how do I get rid to the power 2? Well, that's pretty easy. We multiply both sides by 1/2. So both sides by 1/2. There you go. So what we have here is, of course, this is now cancel out. There you go. We get our Cl. So the next thing we had to do is we had to plug this in here. So the rate 2 is equal to K2 times all this over here. We have K1 Cl2 divided by K 1/2 divided by K reverse, and all this over 1/2. Again, see how I just copy all over? And then what we have here is, of course, Cl, then we have CHCl3. Now let's simplify this. So in this case, we have K cancel out. Well, done. Then we have K2. Then we have concentrated Cl2 to the 1/2. And then CHCl3. Now, if I'm going to type this in the calculator, I would have K Cl2 to the caret symbol 1/2, and then CHCl3. So again, as you can see, this takes a little bit of tedious work, but take the time to write it out, and then save everything last to simplify. Don't try to simplify over here. Bring it over here and simplify it, okay? And if you have any question, please take a picture of your work, and we will see you next time on another exciting chemistry lesson.